Okay, so now we're going to talk about functions of more than two variables, which I have sort of avoided up to this point, just because all the essential ideas can be explained using two variables, and after that it just becomes algebraically more complicated, but conceptually nothing else is really happening. But there's like a small difference that does deserve pointing out. Okay? And so let's think about a function of three variables. And I'm going to even use a slightly different notation, so I'm going to call it t instead of f. So it could be, for example, x squared plus y squared plus c squared. Now, the issue that we do have now in this situation is that if you were trying to represent this function, then the x, y, and z axes have to be used, all of them, for the domain, right? Because now the function depends on three variables. So all of these represent the domain of the function. Meaning that if you actually wanted to see what the graph looks like, you would need to introduce like a fourth axis, which sometimes you would call w. And somehow that axis has to be perpendicular to all the other three. And that's another fancy way to say that you need an extra dimension in order to accurately see the graph of a function of three variables. So the issue for us now is that we don't have access to a graph of the graph of the function. So we can no longer picture So you have to sort of abandon that idea for practical purposes, and you just have to switch interpretations on what you're doing. So this function, instead of just thinking about it as a function, you think about it as a field. Okay? So what's the notion of a field? Well, a field is a quantity, a physical quantity that changes from point to point in space. So for example, what I'm saying is that you should think of this as meaning at the point x, y, z, we measure the value of the quantity t, which equals x squared plus y squared plus c squared. So for example, you can think of this as a temperature function, and this is telling you the value of the temperature at each point x, y, z. So that means that at the origin, the value of the temperature is 0. But if you go to another point, like 1, 1, 1, the value for the temperature that you measure is 3. And if you go to another point, like say -2, 1, 0, well, this doesn't look like that. Let's say this, I don't know. This is so 2, -1, 2. Then the value of temperature that you measure is 4 plus 4, that's 8, that's 9, because you have to add 1. And so now you imagine that all your space is filled up with values for temperature, right? At each point you can make a temperature measurement. You put like a post-it note, like recording the value that you measured, and now suddenly all your space is populated with numbers changing from point to point. And so that's the notion of a field. There's a notion of a vector field, which is one where the same happens, but now you put like an arrow in space at each point. So an arrow here, an arrow here, an arrow here, an arrow here, an arrow here. And that is something that we will exploit more towards the end of the course. So with this interpretation of the function, you can give up the idea of trying to find the graph, and you're just happy with having this representation of thinking that every point in space carries on, like, has the information about the function. Okay, so this point has a value 3 attached to it, this point has a value 0 attached to it, and so on. After that, everything else carries through. It's the same as what we have been doing before. So for example, you can still talk about the partial derivative of t with respect to x, which will be 2x, or the partial derivative of t with respect to c, which will be 2c. And again, if you could really visualize that, if you actually wanted to think in terms of the graph, then that like this would mean, for example, that you are just allowed to move x, okay, and that will somehow give you a wall in this 4-dimensional space that would cut the graph into a line, and that line gives you, the slope of that line would give you the partial derivative, but that's too complicated. What you can just think of is that now the partial, like you have your thermometer with you, you are at a point, you move parallel to the x-axis, meaning that only x is allowed to change. You record the measurements in your thermometer, and the rate of change of those measurements is a partial derivative. There's no need to like appeal to this extra dimension in order to figure out what's happening. Okay? And so like you can take the gradient of a function of 3 variables or even 10 variables. It would just be the collection of partial derivatives. And so again, in this example, the gradient just happens to be 2x to y 2c. Okay, and again, if you are at a point P and you choose some vector at which you're moving, you can still talk about the directional derivative of a scalar field, and the formula is the same as the one from before. Okay, and so here again, B has unit norm. So you see everything still works the same. There's also like a chain rule, multivariable chain rule, nothing changes. Okay, what does deserve some extra discussion is maybe the equation of the tangent plane, and by that I will mean the following. So you might remember that we talked about level curves of a function of 2 variables. Those curves consisted of all the points where consisted of the curves where the value of the function was constant. Okay, for a function of like say 3 variables, it doesn't make a lot of sense to talk about level curves, but instead you can talk about level surfaces. So let's discuss that idea. What's the level surface of a scalar field? So for example, in electrostatics, those are known as equipotential surfaces. Because an equipotential surface is a surface where the value of the electric potential is constant. Okay, so this is a surface where the value of T is constant. Okay. So, for example, if you think of T as temperature, this would be called an isothermal surface, meaning that all the points have the same temperature. If the Earth were an isothermal surface, that just means that for like the temperature function of the universe, then that just means that all the points on the Earth would register the same temperature, which is not the case, right? So we're not an isothermal surface. But for example, for the function that I wrote before, say if you wanted to know all the points where the temperature equals 4, that just means that you have to solve x squared plus y squared plus z squared equals 4, and that actually is the equation of a sphere of radius 2. at the origin, right? Center at the origin. So meaning that if you think about this, here you have a sphere radius 2. And if you move on this sphere of radius 2, if you're only measuring temperature on the sphere of radius 2, then regardless of the point that you choose, you'll measure the value 4. Okay? Now, as you might imagine, the sphere itself is not the graph of a function of two variables, right? This is similar to why the circle is not the graph of a function of one variable. So this is a slightly, it's not the graph of a function, but still it sort of makes sense to talk about the tangent plane to a point of the sphere. Like you can sort of imagine like a tiny tangent plane at each point. And so you would still want to find the equation of the tangent plane. So the point is that in order to find the tangent plane, remember you just have, what does it mean to find the tangent plane to a surface? Oh, so we have this surface which arose from t being constant, right? We think of this surface as consisting of all the points where you made a temperature of T and you got the same answer, right? So you care about a point on this surface, you want to find the tangent plane to this point. I'm giving you a point on the surface, so you just need to know the normal vector, right? Remember that once you know a point and the normal vector, you know the equation of a plane. And so the idea is to use exactly the same argument that we used before for the case of curves, namely that what's if you choose a vector which belongs to this plane, right? What would the directional derivative be of this vector? It would be the dot product of the gradient with the velocity vector, right? But the whole point of this being an isothermal surface, right, is that this should be the instantaneous rate of change that you measure in temperature as you move in that direction. But that direction is a direction on the surface. So because this consists of points with the same value for t, you cannot measure any change in t. So this should be 0 because t is constant on the surface. So that means that the gradient has to be perpendicular to the direction vector. Okay? And so that means that the gradient is perpendicular to t. So gradient perpendicular to the plane and so in other words, the equation of the tangent plane, right, so that means that the normal vector has to be the gradient. So n, and this is the key equation, is the gradient. So in our example for the sphere, right, what's the point on the sphere? This was x squared plus y squared plus c squared equals 4. Right, so let's take the point 1 root of 2, right? That's the point on the sphere of radius 2. Because, yes, this is fine. So what's the tangent plane? Let's say that p equals 1 root of 2. What's the gradient of t? Remember that the gradient of t was 2x, 2y, 2c. And so the normal vector is the gradient evaluated at p. So this is 2, 2 to root 2. And the equation of the tangent plane would be, let's put it here, the tangent plane equation, remember, is just n dot x y z. Sorry, I was just saying that small glitch. The equation of the tangent plane is n dot x y z equals n dot p. So the left hand side just gives you 2x plus 2y plus 2 root 2c, and n dot p, if you do this dot product, you get 8. So that's the equation of the tangent plane. And now that's basically the slight change that happens when you introduce the functions of 3 variables as opposed to functions of 2 variables. You can still keep going, and you can ask, well, what happens with a function of, like, say, 4 variables, like this one? And then what you can do, at least in this case, is still think of like a physical interpretation where now the scalar field depends on time. So it's like a time-dependent scalar field. So for example, you think of the temperature as not being fixed on having that fixed value on a specific point in space, but just changing the temperature throughout the day. And then you can still have functions, you can still have fields that could depend on more variables, but then you just have to be careful about the particular physical situation to make sure that what you're doing makes sense. But again, you don't necessarily try to think about what the graph of this function is, because now this would require 5 dimensions, not just 4, which is what we had before.